Welcome back. Today's goal of this lecture. In my previous video I had seen what is the identity theorem, and use of identity theorem in my previous video I had seen. Also I had seen many different questions which had come in different time in CSR net exam based on identity theorem. Today's goal of this lecture, at first I will see, we all of us know sin square x plus cos square x equal to 1. But today I will say, at first, not only sin square x plus cos square x equal to 1, but also sin square z plus cos square z equal to 1 on the whole complex plane. Also, similar to real, sec squared z minus tan squared z equal to 1 on whole complex plane. Cosec squared z minus cot squared z equal to 1 on whole complex plane. Today, at first I will see this part. Then I will discuss new topic, Schwarz Lemma and Schwarz Lemma. At first see this part. I will say sin squared z plus cos squared z equal to 1. Here I will use identity theorem. We all of us know if fz be an analytic function in a domain D, and if we consider the set S equal to z belongs to D such that f of z equal to gz has a limit point in the domain D, then we can tell fz equal to gz, for this is true for all z belongs to D. Here consider fz equal to sin squared z plus cos squared z and gz equal to 1, and this is true for all z belongs to C. So define S equal to z belongs to D such that f of z equal to g of z. That means S equal to z belongs to C such that sin squared z plus cos squared z equal to 1. And we all of us know sin square x plus cos square x equal to 1, and this is true for all x belongs to R. Therefore, this is equal to R, and limit all point of R is a limit point. So limit point of S is R dash, which is contains the complex number C. So since limit point of S contain complex number, so we can tell fz equal to gz, we can extend it whole complex number. So we can tell sin squared z plus cos squared z equal to 1. This is true on whole complex C. Similarly, squared z minus tan squared z equal to 1, cosec squared z minus cot squared z equal to 1 on whole complex plane C. I hope my all viewers have understood. Okay. Next I will see our main goal of this lecture, Schwarz Lemma. First I will see what is the statement of Schwarz Lemma. At first, D, consider disks, unit disks, but D equal to Z such that modulus of Z less than 1, that means interior of the unit disks, and D closer equal to Z such that modulus of the Z less than equal to 1, that means the only whole unit disks. Here the mapping F from D to D closer is analytic, that means Fz is analytic on the interior mod z less than 1. Since F is mapping from D to D closer and F is analytic on mod z less than 1, then that imply obviously modulus of fz less than equal to 1. Also assume f0 equal to 0. Then by Schwarz lemma we can tell modulus of fz less than equal to modulus of z, and this is true for all modulus of z less than 1. Further, if modulus of fz not equal to modulus of z naught for any z naught with modulus of z naught less than 1, then that imply f is rotation, and since f is rotation, that means fz equal to e to the power I alpha times z. Since given fz is analytic on mod z less than 1, therefore fz is analytic in D, and consider gz equal to new function fz over z when z not equal to 0. Obviously, since gz equal to fz over z when z not equal to 0, that means obviously g is analytic on D omitted with singleton set 0. Since f is analytic in D, that means there exists a power series expansion. Consider fz equal to f0 plus z f dash 0, z square f double dash 0, z cube over 3 factorial f triple dash 0, so on. Since given statement of the Schwarz lemma f0 equal to 0, that means that imply fz equal to z f dash 0 plus z square over 2 factorial f dash f double dash 0 plus z cube over 3 factorial f triple dash 0 plus so on. That imply if we common z, then this would be f dash 0 plus z over 2 factorial f double dash 0 plus z square over 3 factorial f triple dash 0, so on. If we consider this is Az, then obviously this Az is analytic on delta. Therefore, that imply, notice if we divide this fz over z equal to f dash 0 plus z over 2 factorial f double dash 0 plus z square over 3 factorial, here triple f triple dash 0, so on. And this is Az, and fz over z, this is nothing but this is gz. Gz equal to f dash 0 z over 2 factorial f double dash 0 plus z square over 3 factorial f triple dash 0, so on. That means I have got Az equal to Cz. Means Az is analytic on whole D. Therefore, that implies Gz is also analytic at z equal to 0. But here I have seen G is analytic on whole D omitted with 0. That means since Az equal to Gz, therefore we can extend this analyticity at the point 0 also, and in my next video I will see this type of, since here analytic on D omitted with 0 means there exists a singularity at the point at z equal to 0, but here I have also got G is analytic on z equal to 0. That since Az equal to Gz, that means we can extend it G to Az, where Az is analytic on whole D, and this type of singularity is actually removal singularity, which I will see in my next video. What is the removal singularity? Here function not defined at the point 0, but function is analytic at this point. Also bounded on the neighborhood of this point. It is analytic because we can extend it, this analyticity at the point 0 where function has a singularity. We can extend it another function, we can extend this function to new analytic function Az. This type of singularity actually removal singularity, which I will see in my next video. That means I have got G is analytic also at Z equal to 0. That means that implies Gz is analytic on D. That means the function is defined as Gz equal to Fz over Z when Z not equal to 0 and modulus of Z less than 1, and when Z equal to 0 then only F dash 0. If we draw the picture, this is D. Consider this circle with radius r. Modulus of Z equal to r, here I will apply the maximum modulus principle. Mod Gz equal to absolute value of Fz over Z, which is equal to, we can write absolute value of Fz over mod Z. And since on the disc modulus of Z less than equal to r, since by Schwarz Lemma, statement of the Schwarz Lemma, modulus of Fz always less than equal to 1. So this value would be 1 over r. That means absolute value of Gz less than equal to 1 over r. And if r goes to 1 minus, then that implies Gz, modulus of Gz less than 1. And put the value of Gz. Gz means Fz over Z is then equal to 1. That means, that implies modulus of Fz less than equal to modulus of Z. And this is actual the Schwarz Lemma. I hope my all viewers have understood this is. Further condition, let Z0 be such that Z0 less than 1 and Z0 not equal to 0, and absolute value of Fz not equal to Z not, then since Gz equal to absolute value of Fz over Z, that implies absolute value of Gz not equal to 1. That means by maximum modulus principle, we all of us know, when function is non-constant, then G attains maximum on the boundary of the unit disc. But here I have got modulus of Gz not equal to 1. So by maximum principle, since G attain by maximum, when function is non-constant, that means function maximum value on the boundary, that implies G is constant by maximum modulus principle with modulus 1. That means Gz equal to e to the power I alpha, and since Gz equal to e to the power I alpha, that means Fz equal to Z times e to the power I alpha. And we all of us know if fz equal to z times e to the power I alpha, that means f is actually a rotation. I hope my all viewers have understood the Schwarz Lemma. That means by Schwarz Lemma, if f is mapping from D to D closure, then f is which is analytic. That means obviously f is analytic on mod z less than 1, and that imply modulus of fz would be less than equal to 1 since it is mapping from D to D closure. And in Schwarz Lemma here assumed also f0 equal to 0. Then by Schwarz Lemma we can tell modulus of fz less than equal to modulus of z, and this is true for all modulus of z less than 1. That means by Schwarz Lemma this is actually strictly contractive, because modulus of fz less than equal to modulus of z, and when equality sign modulus of fz equal to modulus of z, then f has a rotation, and this is true for all z. When modulus of fz equal to modulus of z, that means this is not contractive. Otherwise modulus of fz would be modulus of z, that means this is actually strictly contractive. I hope my all viewers have understood this lemma. Means when equality holds for some non-zero z, that means that imply fz equal to c times z, where for some c with the condition modulus of c equal to 1. Furthermore, by Schwarz Lemma we can tell absolute value of f prime 0 always less than equal to 1, because since here f0 equal to 0, so here fz equal to such type a1j, a2j, so on, where a1 means f prime 0, a2 means f double prime 0 over 2 factorial, so on. Then since here by Schwarz Lemma we can tell absolute value of f prime 0 less than equal to 1, then f prime z would be a1 plus 2a2z plus 3a2z square, so on. Then if we apply mod both sides, then modulus of f prime z would be modulus of a1 plus 2a2 modulus of z plus 3a2 modulus of z square, so on. And at z equal to 0, this value would be f prime 0 would be less than equal to a1, and we all of us know this type of coefficient always less than equal to 1. So f prime 0 always less than equal to 1. That means by Schwarz Lemma I have got modulus of fz less than equal to modulus of z. Also extra condition modulus of f prime 0 always less than equal to 1. This is the extra condition of Schwarz Lemma. I hope my all viewers have understood. Now I will see some exercise on this lemma. See one example which had come since a net exam. D equal to z belongs to complex number such that modulus of z less than 1. Then which of the following statement is true? There exists a holomorphic function f from D to D closure with the condition f0 equal to 0 with the property f prime 0 equal to half, second f of 1/3 equal to 1 over 4, third f of 1/3 equal to half, fourth f prime 0 equal to sec pi over 6. Which of the following be true option? Notice this is the Schwarz lemma. This is actually the application of Schwarz lemma. Since here mapping f from d to d closure and f0 equal to 0. Therefore, by Schwarz lemma, we all of us know modulus of fz less than equal to modulus of z and f prime 0 less than equal to 1. Therefore, by Schwarz lemma, here f prime 0 equal to half, which is obviously less than 1. So option 1 is a right option. And modulus of fz less than equal to modulus of z. Second, given f of 1/3 equal to 1/4. Obviously this is right option because modulus of fz less than equal to modulus of z. But third option, f of 1/3 equal to modulus of f of 1/3 equal to half, this is not be true. And option 4, f prime 0 equal to sec pi over 6, which means 2 over root 3, which not be less than 1. So option 4 also wrong option. That means only one option, option 1 and option 2 is a right option. I hope my all viewers have understood this is okay. Well, today I will stop here. In my next video, I will discuss more application of Schwarz lemma and identity theorem, because this theorem, Schwarz lemma and identity theorem, is more important for higher study of complex analysis, also for all competitive exam. Okay, see you soon. Stay safe and stay positive always, and don't forget to subscribe my channel for more videos. Thank you so much.